Okay. So let's have a look. Let's look at a rational function again, like we did yesterday. So let's take one. I'm trying to make up a little better one this time. Let's do something like, how about f of x equals x squared plus 2 over x minus 3. Okay. So what do we want to get the domain first? All right, what's our domain?
Anything about 3.
Okay, so x cannot equal 3. So when we make our table, we'll just exclude 3. Okay, let's get everything for this one. Concavity, points of inflection, all that stuff. So we need derivatives, right? So first derivative. A little quotient rule. What do you think? Liz, want to help us out with a little quotient rule here? Low-D high. So what do we got here?
X minus 3 times 2x.
Good, good. Minus,
Square plus 2.
good. Okay, all divided by,
X minus 1.
good. So if we simplify that, what are we going to get? I distribute the 2x, I'm going to get 2x squared minus x squared gives me an x squared. 2x times negative 3 is negative 6x. And then minus 2. You guys check me on that. Does that seem right?
Yes.
Okay. On the bottom, x minus 3 squared. So there's our first derivative. Okay. Do we have any places where, do we have any first derivative critical numbers?
No.
Let's talk about that.
The negative is critical.
Go ahead, Kirk, what do you say?
There, I mean, 3 is a critical number, that's also a critical number. First.
Okay, so 3 is not in the domain, so it can't be a critical number, right? Critical numbers are only values of x in our domain. We're only looking for derivatives where the function exists, right? So 3 is disqualified. That would have been a critical number because it's a 0 of the denominator. Good. Numerator, we'd have to find them using, to solve that quadratic equation, right? So we end up with f prime equals 0 when x squared minus 6x minus 2 equals 0, right? So we got to solve that quadratic equation, okay? How are we going to do that? Probably quadratic formula. Everybody agree? We can't factor that. So if we use the quadratic formula, we're going to get x equals negative b plus or minus square root b squared minus 4 times a times c. Well, that's minus negative 8, right? So plus 8 all over 2. So that's going to give me 6 over 2 is 3 plus or minus the square root of 44. So what is that? 2 radical 11?
Yeah.
Over 2. So it's radical 11. Okay, so what are those? Just real quick, somebody just give me, let's put in decimal equivalents. What do those work out to be as decimals? So x is roughly equal to, put it in your calculator, what does that work out to be? 3 plus the square root of 11 is about what?
6.63.
Okay,
Oh.
or,
That's, oh, my bad, never mind, I did 2 radical
seems a little bit, what is that? So
6.3, 6.32.
Okay.
The plus.
Okay. 6.3, or what if I subtract?
Negative 1.32.
Okay. Roughly, we just want to get an idea, right? From our table. Okay, good, good. So there's our first derivative stuff. We get 2 critical numbers. Okay, second derivative. So we'll just differentiate this quotient, right? So what's that going to give us? So let's help us out here. What do you think? Ryan, give me a quotient rule for the first derivative.
X
minus 3 squared
Good.
times 2x minus 6.
Okay. Minus,
Minus x squared minus 6x minus 2 times 2 times quantity of x minus 3.
good. All divided by,
All divided by x minus 3.
okay, so now we get common factors that we can factor out here, right, from each term. Let me see, we've got two terms. I've got the term, first term comes from the first part of the product rule, second term comes from the second part, right? So here's a little shortcut we can take, and there's a good way to kind of show your work when you're doing this stuff. So I could factor out an x minus 3, that's my common base, correct? I can only take out one power though, but look, I've got x minus 3's on the bottom. So what do? If I factor out and cancel at the same time, you with me on that? What's the result?
X minus 3 is third.
So on the bottom, I'm gonna cancel 1, and that's gonna become a 3. On the top, that one's gonna go away, and one of those is gonna go away. Are you with me? Okay?
Didn't we also just factor out 2x minus 6 instead of that? You distribute the 2 with the second round?
Well, I mean, yeah, we could, but we're gonna end up having, I mean, we could take a 2 out of everything too. There's a 2 there, and I could take a 2 out of that if I want to. That's fine. We can do that. So if I factor a 2 out, on the top I'm gonna get a 2, then what am I left with? X minus 3 times x minus 3, right? Everybody see that? Minus, and then this 2's gone, it's out front, right? Is that gonna be confusing to do that? Factor, everybody see, we took that 2 out, let me kind of color code that. So we took this 2, and we factored a 2 out of this guy right here. We made that 2 times x minus 3. We took those 2's out front. Right. So then we're left with x minus 3 times x minus 3 minus the quantity x squared minus 6x minus 2, and we can simplify all that. That's our numerator. So what do we get then? If I expand that out, x minus 3 squared is just going to be x squared minus 6x plus 9, right? Minus x squared minus 6x minus 2. So a lot of that stuff cancels, right? So I get the x squareds cancel, the negative 6's cancel, and I get 9 minus negative 2. So on the top, I just get 2 times 11. You see that?
6 is canceled, it's a minus negative 6, right?
Right. I get a negative 6 minus a negative 6, so we cancel. 9 minus negative 2 is just going to give me, so when all the dust settled there, really what I ended up getting was just a 2 times 11 on the top, right? So 22 over x minus 3 quantity cubed. Are there any second derivative critical numbers? No, none. So this also is kind of a boring function, right? We get a couple first derivative critical numbers, but no second derivative critical numbers, so there will be no inflection points, right? And now we can just reflect all the stuff in our table. And so we've got, what was our, 3 was the one value of x we had to exclude from our domain. So at 3, the function was undefined. What happened there? Look at the original function at 3.
It's a 0,
Zero of the denominator, but not the numerator, right? So what's that tell us? Is zero at the bottom but not the top? Vertical asymptote. So we know right away here, we're gonna split this thing into two pieces. Right? Got a left half and a right half. And our critical numbers then were about 6.3. So out here at, somewhere out at 6.3 and at negative 0.3-ish. We get a zero of the first derivative. Okay, and we don't get any zeros of the second derivative, but we've got our second derivative here, so we could evaluate, we could apply the second derivative test, because we went through the hassle of finding the second derivative, right? So if that's our second derivative, let's summarize that. So f double prime equals 22 over x minus 3 cubed. What's the sign going to be at 6.3?
The same as
Top's positive, bottom's positive, right? Positive over positive is positive. What about at negative 0.33? Positive over negative. I get a negative number cubed is negative. Positive over negative is negative. Okay? Could there be any other, so why did explain something to me here. This is kind of an interesting, it's to pull some things together. We got no second derivative critical numbers, right? So is there any place where the second derivative could change signs?
no.
But it did. How come?
Awesome.
Right? Because the asymptote divides this into separate universes, right? So the asymptote is still a place where the function gets completely split apart, and so we could get differing behaviors on either side of the asymptote, right? Still without having a critical number, okay? Okay, so then what is this one, Lily Y? What do we get going on here by the second derivative test? If I have a zero first derivative and a positive second derivative, what's that telling me is going on there? A horizontal tangent, positive second derivative.
Concavity.
Okay, what concave? Somebody help her out.
Down.
It's gonna have to be minimum, isn't it, right? Because I have positive concavity and a horizontal tangent. So by the second derivative test, that's drawing us a picture of, right? Does that make sense? And so over here then, I've got zero first derivative is horizontal tangent. I've got a negative concavity, and then our little trick, remember, is it's a sad function and a happy function, right? You just know right away. That's a quick way to just remember, okay? So we got extrema there. We get no points of inflection. Okay, so that's all pretty good. So we got lots of stuff. Now, what about, we have a rational function, so we can also do a limit at infinity. Okay, here's the part that we haven't really talked about this year yet, but we did this in Algebra 2. Do you remember what happens? We had our three rules we reviewed yesterday. If we take the limit of a rational function at positive or negative infinity, if the bottom is a higher order polynomial than the top, we just get an asymptote at y equals 0, right? If they're equal order polynomials, we get a horizontal asymptote where y equals the ratio of the leading coefficients. And if the top is a higher order than the bottom, then we don't get any horizontal asymptotes, right? At the beginning of the year, we called that no limit. And it was, there is no limit, right? But do you remember what happens if the top is one order higher than the bottom? From clear back from, yeah, you guys remember that? Did you talk about that last year? Oh, you did talk about it last year a little bit?
Yeah.
I was really impressed you remembered it all the way from Honors Algebra 2. Okay, so if we take this, let's review how we do that. Maybe we mentioned that this year too. I think we probably mentioned it, but I don't think we've done a lot with it. Okay, so how do we come up with that slant asymptote? Okay, we divide it out. We simplify the quotient, and we can use synthetic division here, right?
Yeah.
I reviewed how to do synthetic division with like fractional zeros, right? You guys? I think I did, but if I haven't, we'll do one of those too at some point. I want to make sure you guys know how to do that. So if we do this synthetic division problem, what are the coefficients on the top?
1, 2.
No? What is it? 1, 0, 2? You have to hold a column for all the powers of x. And what's the 0, the denominator?
3.
Okay, and so then we're going to bring down the 1. 1 times 3 is 3. We add with synthetic processes, right? So we get 3, 9, and 11, right? So this is equal to, remember what this is telling us, these are coefficients, right? So this is telling us that we're going to get a 1x squared plus,
It'll just be x plus 3.
oh, sorry, x plus 3, so what am I doing? Yeah, not x squared. We get 1x plus 3, I guess I can put the 1 there, right? There's my coefficients. Plus, the 11 is what remains over our denominator of x minus 3, right? Okay, what's the advantage of that? How does that give us a slant asymptote?
That's the function sequence.
It's the equation of a line, but here's the part you guys didn't talk about last year, probably, I guess, right? We did a little bit of limit, we actually did limits in algebra too. Remember doing the limit notation? Probably don't remember that. It probably don't know. But here's why I did it, because I knew you guys were all going to calculus, and I wanted you to, this is where it comes in handy. When we do that synthetic division process, watch this, the limit of f of x, we'll use this form. We get the limit of x plus 3 plus 11 over x plus 3 as x approaches plus or minus infinity, right? So I can put a limit there. Okay, well, what do we know about that ratio? It goes to 0, exactly, right? In the limit, as x goes to infinity, that ratio, by our rules that we established earlier in the year, our rules for limits of rational functions, infinite limits of rational functions, that goes to 0, and we just end up with x plus 3. Now, in the limit that x goes to infinity, that gets infinitely big in this case. If it goes to negative infinity, it gets negative infinitely big, right? But, so there is no limit, but it gives us the shape of the asymptote, right? So if we go back to our table, is there a good place to put this in the table? Not really. This is the one part. If you get horizontal asymptotes, they fit in there great. But this is one where we just kind of add that, just kind of separately someplace on here. We'll just write slant asymptote y equals, what was it, x?
Plus 3.
Plus 3. And now everything's in our table, right? So if we want to make a sketch of this thing.
So we don't even include the remainder?
No, we don't want it, because we're taking infinite limits, right? The whole point is we want to get the skeleton of this thing. We want to get the asymptotes out. Once you get the asymptotes up there, it gets really easy to draw a function, because you know the function has to adhere to those asymptotes. And so it eliminates a lot of possibilities, right? Okay, we've done it a few times before, but I'll prove my point again here with this. So if we graph this guy, here's our x-axis, y-axis will go right in here somewhere, right? And so we've got out here, we got our slant asymptote was y equals x plus 3. So that's just going to be, it's going to go through 3 with a slope of 1, so it's going to look something like that. There's our slant asymptote. Okay. We had a vertical asymptote where? 3. Okay, so out here at 3, we have a vertical asymptote. And that, not much can happen there, then, right? If we know that we're supposed to get a maximum at negative 0.3, so right in there somewhere, and we could easily figure out what the y value is if we want to. We could just plug that into the function and figure out what y is. Let's not mess with it. We don't need to be that specific. But what's that tell us that the shape has to be to the left of this vertical asymptote?
Down.
It's gotta be concave down, and it's gotta have that maximum we were talking about, has gotta be at like negative 1/3. So someplace right in there, we're gonna get a maximum, and then this thing has to just go like that, doesn't it? See how those asymptotes help? It's like you get the skeleton of the function, then you just kind of fill in some details, right? How about over here? Well, we know that we're gonna have a minimum. I didn't draw this big enough, but we're gonna have a minimum up here, like where's it supposed to be at 6, so I guess, maybe I did. 1, 5, 6, so up there or something, I guess I did. So this one's just gonna look like that. Right? Make sense? All right. The one other one I kind of wanted to show you guys, because these are the ones that I just remember having trouble with these in college, because we never did a bunch of these in high school, and that's piecewise functions. So what if like an absolute value function? Because they come up and then they're never really fun to do, but if you haven't ever looked at them, they're really hard to do. So let's do one, kind of a hard one. We may not finish it today. But this is probably the last one, unless you want to go through a trig function, another trig function. This is the last one I kind of thought I would do. So what if we take the function like y equals absolute value of x squared, let's do plus x minus 6. How about? All the stuff. We're going to make a table and sketch this function. It gets hard because it's absolute value, right? But what do we always do with an absolute value function? We got to make, well, at least two. We got to make a piecewise function out of it, right? Does that make sense? We know that by definition, the absolute value of a equals a whenever a is positive, and negative a whenever a is negative, and 0 whenever a is 0, right? Make sense? So we'd have to look at this and we'd have to ask ourselves, the argument of that absolute value, meaning what goes inside it, the x squared plus x minus 6. All the places where that is positive, it's just going to equal that expression. But all the places where that expression is negative, the absolute value function has to equal its opposite. See what I'm saying? Okay, so what are some ways, and there's no one way to do this. I'll show you kind of a good trick for this, but how are you going to analyze that? How are we going to analyze that function? Let's just take that function by itself in this first page, and let's just see if we can figure out where it's positive and where it's negative. How are we going to do that? I mean, one way we could do this, we could just start off with an inequality, right? We might ask the question, where is it positive? So we could say something like, where is x squared plus x minus 6 greater than 0? Okay, what are some ideas here? I really just, you know, there's a bunch of different ways we can approach this. I might point you towards a better way at the end, but thinking about this kind of stuff makes you good.
Just factoring it.
Yeah, we could factor it, right? So one way we could do this is we could factor this, because it does factor.
X plus 2, x minus 3. I mean, x plus 3, x plus 2.
Okay. Right? So now what? If we look at that function, x plus 3 times x minus 2, where are the zeros of that function? Where does it equal 0? Okay, okay. 2 and negative 3, right? So if I were to make let's just say we've got our zeros at -3 and +2. Here's one way to represent functions like this, like factorable absolute value functions. So we could say, let's look at the behaviors of those factors, because we do this stuff a lot, don't we? Whenever we try to evaluate the sign of a derivative at a point, we like it to be in factored form, because then all we have to think about is that positive or negative, is that positive or negative, and we get a simple product rule. See where I'm going with that? So what if we take something like, let's say, the factor x plus 3. X plus 3 is going to break, it's going to equal 0 on this one right here, isn't it? Right? And x equals -3. When x is less than -3, what's the sign of that factor going to be? See what I'm saying? If we look at the behavior of this function, in fact, let's even call it something. Let's call it h. Let's say h equals x plus 3. Well, what's the sign of h to the left of -3? Like if I plug -4 in, what do I get? Positive or negative? Negative. So over here, it's all going to be negative. Up here, though, for values greater than 3, -3, it's always going to be positive, isn't it? Right? Okay, how about, call it g equals x minus 2. That's going to equal 0 at +2. To the left of that, we get what? Negatives. To the right of that, we get positives. Right? So now let's look at the combined behavior. If we take f of x, which is a combination of both of those things, right? It's g times h. What does our sign rule tell us?
It's less than 2, it's negative.
Negative times negative is positive. So over here, it's going to be positive. Negative times positive is negative. Positive times positive is positive, right? So that gives us the sign behavior of our overall function, doesn't it? Right? Could we do that another way? Yeah, we could. We could. How else could we solve this? Well, we could do something like, what if we completed the square or something, right? That's, to me, that's a really good way to do it algebraically. This is kind of an awkward algebra approach, but it works really well, because you could have arbitrarily many factors here, and you're just going to look at the overall sign products of all those different regions, right? It's a pretty good way to do it. But we could also, if we wanted to just take this thing and complete the square, the absolute value of x squared plus x minus 6, what would that look like if we completed the square? That's the absolute value of x squared plus x plus 1 minus 7, right? I'll do that right. It seems like it should work to me. It's such a good idea. Yes. Oh, hang on, never mind. I messed that up already. So you guys remember when you complete the square? So we'll come back to this one. Let's come back to this one if we have time. I feel like I'm gonna get off on too big a tangent. Seems like that'd be a pretty good idea. I could be wrong too. Okay, so we got this. This is our behavior, right? So then we know that if we wrote down our piecewise function, the absolute value of x squared plus x minus 6 equals, let's write this out as a piecewise function. So when x is greater than 2, it equals itself, right? So it's positive. When x is equal to 2, it would be 0. When x is between -3 and 2, it's its opposite, right? So it would be, the opposite would be negative x squared minus x plus 6, when x is negative 3. It's 0, and then finally, when x is less than negative 3, it's positive again. Right? So there's our absolute value function as a piecewise function. Now what do we do to differentiate?
Differentiate each of them individually.
Yeah, just differentiate each piece, right? Okay. Remember doing this stuff at the beginning of the year? We did a couple of these. When we talked about the nature of a derivative, where derivatives are exist and where they don't exist at sharp corners. We looked at some examples like this where we saw that in some cases we could get sharp corners here, and so we get places where the derivative doesn't exist. Those would be critical points now, wouldn't it? Critical numbers for us. So if we differentiate, this was f prime of x, then would equal the piecewise function. What do we get up there? What's the derivative of x squared plus x minus 6? 2x plus 1, good. Okay. What's the derivative of this? Of this middle section?
Negative 2x minus 1.
And the derivative of the bottom would be the same, right, for this bottom section. Okay? All right, so then what's going on here? And this is kind of an important point that gets glossed over a lot. What's happening at x equals 2? Does the derivative exist there or not? What do you think?
It's undefined.
Maybe. How do you know? Ryan, how would you check to see? Any idea? We get the derivative when x is greater than 2, that's our derivative function. When it's less than 2, that's our derivative. Between 2 and negative 3, that's our derivative function. Why would it not exist at 2? Why would it not exist there? What would have to happen for it not to exist there? Sharp corner, right? Okay. If it's a sharp corner, think what that means. As the ant walks towards 2 from the left and from the right, he's going to sense different slopes from the left and from the right. Okay, here's the connection I really want to make, and this is a tough one. This is really a hard one to grasp, but how are we going to know what the ant's slope sensor says as he approaches 2 from the right? What do? You're probably thinking you want to plug 2 into the derivative, right? But we can't do that because 2 is a transition point. So what do we do when we come up to transition points with a function? We can't plug in 2, but what can we do? Take a limit, right? We'll take a limit of the derivative as x approaches 2 from the right, and a limit of the derivative as x approaches 2 from the left, right? Because that's telling us what, as the ant is about to step on 2 from the left and the right, what is his slope sensor saying, right? And then we'll compare those values. What if they're the same? If they're the same, we're fine, right? If they're the same, then that means that there is no sharp corner, and so the derivative exists there. If they're different, though, that means that there's got to be a sharp corner, because we're going from one slope instantaneously to a different slope when we cross through 2, right? You get the idea? Okay, so that we have yet to determine. So we'd have to do, in order to find out what goes there, we have to do the limit of 2x plus 1 as x approaches 2 from above, from the right. What is that limit? 5. We agree? And we have to compare that to different color. The limit of negative 2, so now we're down in this part, right? The limit of negative 2x minus 1 as x approaches 2 from the left, what's that equal to? So the limits don't agree, do they? Right? When he's approaching from the right, he thinks the slope he experiences as he walks into 2 is positive 5. As he's approaching 2 from the left, he's seeing a different slope, and so the jury is out now, or the jury is settled. This is one where, at this point right here, when x equals 2, there is no limit, right? There's no derivative, okay? It's undefined because they get a sharp corner. Okay. We could do the same thing up here, and maybe we can just kind of power through this one in our head. As we approach -3 from the right, if I take that limit, I'm going to get positive 6 minus 1 is 5. As I approach -3 from the left, I'm going to evaluate the limit at this limit at -3, and I'm going to get -6 plus 1 is -5. Right? Once again, I get different values, don't I? Right? Because the limits don't exist, or they don't equal each other. Because the limit of f of x as x approaches -3 from the left is not equal to the limit of f of x as x approaches -3 from the right. Once again, at x equals -3, it's undefined. Okay, tricky, huh? So we do get some critical numbers here, don't we? We get critical numbers at 2 and -3. We get any other critical numbers, because we get critical numbers where the derivative is undefined or where it equals 0. So you got to be tricky. You got to be careful with this one too. Where does 2x plus 1 equal 0? At -1/2. Well, is 2x plus 1 the definition of the function where x equals -1/2? It's not, is it? Because x equals -1/2 in this region right here. See what I'm saying? Okay. So this part of the behavior, the 2x plus 1 part of the behavior, there is no 0 of that function on this interval, and there's no 0 of that function on its domain. Okay, let's look at the middle one. Where does -2x minus 1 equal 0? At 1/2. Do I agree? Is 1/2 on this interval?
Yes.
It is, right? So there is actually 1 0 of the function, and it occurs on this piece right here. Okay? These are tricky. They really are pretty tricky. So we get, down here, we get f prime equals 0 in here at x equals 1/2. So now we got all that stuff that we can put into our table, right? So let's start our table. When are we out of here, like in 4 minutes?
Yeah.
Okay, so this will leak over a little bit into tomorrow. But I do want to I want you to see one of these, I really do. Just trust me on this one. This is a good one to see. So, and even if this, let's take a pause for a second here and just talk metacognitively for a second. Even if this stuff doesn't make complete sense this year, I can tell you that, like my sister, who's got a PhD, very, very smart person, she either flunked or got a D in organic chemistry the first time she took it. It's a hard class. She didn't think she got much out of it, but she went back and took it again, and what'd she get? Got an A+, yeah. I mean, so it really, even if you don't think you get all this stuff the first time through, I promise you that there's a lot of connections being formed, and you're more receptive to it the second time. So this is one of those things where I'm just telling you, it's good to see this before you go to college. So what did we say about this? Our function, we had zeros at, or hang on, we had critical numbers at where? We had critical numbers at 2 and -3, right? And those were critical numbers where the first derivative was undefined, right? We had a 0 also at, wasn't it 1/2? At x equals 1/2, we got a 0 of the first derivative. okay? What about, is it worth doing a second derivative? Because we always say, I mean, pretend we didn't even have to. We do, but what if we didn't? Would this be an easy one to differentiate to take a second derivative?
No.
I'd say yeah, super easy, because all you gotta do is just differentiate each of those pieces, right? So the second derivative is really pretty simple. What's the second derivative equal? Well, what's the derivative of 2x plus 1? 2. So it's 2 when x is greater than 2. It's negative 2 when x is pinched between negative 3 and 2, and it's positive 2 when x is less than negative 3, right? And then in between, the first derivative doesn't exist, and so therefore the second derivative we wouldn't even take, right? We don't even worry about it, because where the first derivative is undefined, we don't worry about the second derivative. That's not part of the domain of the second derivative then. In the same way that if the function's undefined, we don't worry about derivatives where the function's undefined, right? Okay? So we can go to our table then, and we don't even care that it's 2. We just know that that's negative and those were positive.